All right. So what we're going to talk about today is using nodal and mesh analysis in the frequency domain, which, by the way, just follows the exact same rules that it did in the time domain, DC circuits, and all of that kind of good stuff. So really, we're just going to have a brief refresher on that, and then we are going to use MathCAD to solve the system of equations using complex numbers so that you guys have some idea of how to do it, and I can talk to you about some pitfalls and problems and all that kind of jazz. So as part of what we're doing here, we're going to wind up answering all of the questions for the ICA and all that kind of stuff anyway, because our goal is to effectively just solve this whole thing, not just write the equations so that we can use MathCAD for things. Okay. So let's take a crack at this guy using nodal analysis where I already have. So I chose to put ground at the bottom node on this to make us work and remember how supernodes work and all of that kind of good stuff, right? So we have two voltage sources in this circuit, so I should expect to get two voltage relationship equations. Can anybody remind me of how the voltage relationship equations work for a voltage source? Camden. Absolutely right. Okay. So for the voltage relationship equations, it's just whatever nodal voltage is at the positive polarity terminal of voltage minus whatever nodal voltage is at the negative polarity terminal of the voltage source. So we can do something similar for that dependent source over there on the right. So that's going to look like 3ix would be V5 minus V6. Okay. So those are our voltage relationship equations. Let's go ahead and figure out what Ix and Vx are in terms of our nodal voltages as well. So Ix is one of those tricky ones that I like to throw at you guys. It's the current that's flowing through a voltage source, and I like to throw those at you guys because it makes you think about the relationships and all of that kind of stuff. So how might we choose to express that current Ix? Anybody have any thoughts? So it could be equal to the currents entering the node. So that would be this current flowing down, this current flowing up, and this current flowing to the right. Absolutely. So the current flowing down looks like V2 minus V5 over 7. The current flowing to the right looks like V4 minus V5 over negative J5. And the current flowing up looks like negative V5 over 4 ohms. Is there another relationship that we could use? It's maybe a little less gross. Camden? Sure. So instead of saying the current flowing in equals to the current flowing out to find Ix, we could also consider that the current Ix is flowing into the node where we have V6 labeled. So it must equal to these two currents flowing out as well. So it could also be expressed as 2 angle 0 degrees amps plus V6 over J6 ohms. And because that's a smaller representation, it's got less terms and all of that kind of stuff, that's usually what I would wind up using just because it's going to make the math a little easier, right? So either of those are fair game. Vx is also, well, actually, because we're doing nodal analysis, Vx is going to be pretty easy. If we were doing mesh analysis, Vx would be a pain in the butt, which is what we're going to do next. So how would I express Vx in terms of my nodal voltages? V2 minus V1, absolutely. Doesn't need to be any more difficult than that. All right. So we've got 4 equations. It seems to me like we need a couple of KCL equations in here somewhere, right? So let me think about how many variables we have total. 6 plus Vx plus Ix, 8. So we're halfway there, right? So the first KCL equation that I'm going to write is the currents that are leaving my supernode between nodes 1 and 3. So that would be this current, oops, and this current. I'm going to add all 3 of those together, set them equal to 0. Everybody understand why we're adding these 3 currents together? That's the currents that are leaving our supernode, okay? So let's talk about the one flowing down through the J3 ohm inductance first. That's just going to look like V3 over J3 ohms. Then we'll do the one flowing to the right through the 1 ohm resistor. So that'll be V3 minus V4 over 1 ohm. And then lastly, we have the current flowing out of the positive polarity terminal of that voltage source down through the minus J2 ohm capacitor, excuse me. So it's going to look like V1 minus V4 over negative J2. We can go ahead and take care of our other supernode as well. So this will be the currents that are leaving my supernode over here on the right, which would be this current, this current, this current, this current, and this current. That supernode is between nodes 5 and 6. So starting with the currents on the left, we're going to have V5 minus V2 over 7. Then we'll have V5 minus V4 over negative J5. Then we'll have V5 over 4 ohms. And then 2 angle 0 degrees amps. And V6 over J6. 5 terms for 5 currents, so all that seems legit. What do we do next? V6 over J6. All right, so scrolling back, what should we be doing next? We've got 6 equations, we need 2 more. V4 and V2, so KCL at node 4 and KCL at node 2, absolutely. So KCL at 4 is going to be these 4 currents. So starting with the current flowing up, we're going to have V4 minus V1 over negative J2. With the current flowing to the right, we're going to have V4 minus V5 over negative J5. Current flowing down is going to look like negative 2Vx. And then the current flowing to the left is going to look like V4 minus V3 over 1 ohm. And lastly, we need our KCL at node 2. So this one's going to be pretty straightforward. It's going to be this current plus this current. So that's going to look like V2 minus V5 over 7. Minus 2 angle 0 degrees amps. So those are all of our relationships, just using mesh analysis. We now have everything that we could possibly need because we have 8 equations and 8 unknowns. So it's time to break out good old math. Where's my phone? So move this out of the way. Throwing a solve block in here. So I'm going to start with my voltage V1. And you don't necessarily have to use the parentheses like I'm using here, but I think it's good practice, and we'll see why in a moment. I'm just going to guess that it is a polar form 1 angle 0 degrees full. Okay. So the 1 is easy. If we look here in the operators menu and we go down to engineering, we can see a couple of things really quickly. First, here's how we get to the angle operator. It has a keyboard shortcut, Control-Shift-P. That's what you're going to see me do every time. I'm never going to click this button because it's annoying. Moving over here to the left, this is the degree symbol. It does not have a keyboard shortcut, which is wildly annoying. So instead of using this, we're going to type in the letters DEG because MathCAD knows to interpret that as an angle in degrees. Because having to go in and out of menus constantly is going to make me annoyed. So 1 Control-Shift-P, 0 DEG. Outside of the parentheses, I'm going to explicitly multiply by the units of a volt. I am never not going to explicitly multiply because we're going to have so many parentheses and all of that kind of stuff that it's so easy for MathCAD to accidentally interpret things as a function. We're going to explicitly multiply everything so that we don't run into constant issues with that stuff, okay? So I'm going to do the same thing for V2. And I'll put a V3 over here as well, and I'm just going to keep on trucking. If you guys have any questions about how I'm doing this, please ask. So I've got my nodal voltages done. Now I'm also going to put a guess value for Vx. Same thing, 1 angle 0 degrees volts. And then I have a current, I think I named it Ix, and I'm just going to do that one 1 angle 0 degrees amps. So those are all my guess values. So I've defined all my variables in my system. Now I'm going to start writing my equations. So the first equation that we came up with was a voltage relationship equation where we said 12 angle 0 degrees volts must be equal to V1 minus V3, I think. You can go back and look at that. Yep, V1 minus V3. The next one that I'm going to do is this 3Ix. Notice that this is a current controlled voltage source, so that 3 has implied units of volts per amp. So for my next equation, I'm going to have 3 volts per amp times Ix will be equal to V5 minus V6. Then I'm going to write my equation that's defining Ix, because I think I did that one first, and I'm going to do the smaller one, so 2 angle 0 degrees amps plus V6 over, that says VG, not V6. J6. So in MathCAD, much like your calculators, you don't put the J out front. You put the J afterwards. MathCAD is actually pretty great though, in as much as it recognizes J as the imaginary operator, just like it recognizes I as the imaginary operator. So what I'm about to do here is I'm going to type in my omega symbol, and I want you to notice that something happens. So right now, the J is not italicized, right? So that means that it's interpreting that as square root of -1. If I then follow this with a character, it makes it italicized. So it's treating that J omega, or J capital omega, or J ohms as a single entity, which is not correct, okay? So going back here, 6J times the unit omega is what's going to make MathCAD interpret this as an impedance. Okay? So it's very, very important that we remember to multiply often in these things. All right, now we have our relationship for Vx. So that was V2 minus V1. It is not. Thank you for that, Ashton. So this equal sign right here should be the control equals, because this is one of our constraint equations. So thank you for that. V2 minus V1. And looks like I'm ready for my KCL equations. So before I start cranking those out, does anybody have any questions about what I've done or why I've done it to this point? And thank you so much for catching that mistake, Ashton. Yes.
Like anti-engineering, but why do people with the units? I just feel like they're so annoying. I don't think just
because I'm a good engineer.
I always just like wrote the equation.
So particularly in this class where you have web work that's expecting answers that are in specified units, this just helps me make sure that I'm going to be able to get an answer in the units that I want. Okay. That's really it.
Yeah,
I'm a huge proponent. Yeah, like I'm a huge proponent of using units throughout everything. I think I've harped on that numerous times throughout the duration of this class. It is always good practice. Just as an anecdotal thing, how many of you might be too young, some of you guys, but Ashton and I aren't, although I'm significantly older than her. The Hubble telescope. Anybody remember any bad things about the Hubble telescope? So apparently you guys are too young for that. But the Hubble telescope was a billion-dollar space platform that was developed to look at images out in space. And turns out that there was a few $100 million error in the manufacturing of it because units were not included. So literally they had to go back and like regrind out this huge mirror because the correct units were not put in for the tolerances. And it caused all of the images that were originally generated by this thing to be like incredibly blurry and unusable. So units are good. Alrighty. Any other questions other than
Like, that happened. Whoever designed it, it was that.
it was on the designers for not including units and not paying attention in their calculations? So somebody or probably a whole team at NASA lost their job. All right. So let's burn through our KCL equations. So at supernode 1,3, we're going to have V3 over J3. So Shift W to give you the capital W, and then Control G to convert that capital W into its Greek counterpart, capital Omega. Yep. And then V3 minus V4 over 1 ohm. And then V1 minus V4 over negative J2 ohms. Is equal to 0. And then we're going to do our next one. This one's big and gross. So V5 minus V2 over 7. And then V5 minus V4 over negative J5. And then V5 over 4. And then 2 angle 0 degrees amps. And then V6 over J6. And one last equation. Oh, no, 2 more equations. Dang, miscounted. V4 minus V1 over minus J2. V4 minus V5 over minus J5. Thank you. That should definitely be control equals to 0. What? Yeah, I don't know why I keep doing G instead of the number 6. Very different keys on the keyboard though, so. Let's see, minus 2Vx. So let's look at this really quickly. So this is a voltage controlled current source. So the 2 here has units of amps per volt. And then my last term here, V4 minus V3 over 1. Control equals to 0. Now I'm on my last equation. So that's going to look like V2 minus V5 over 7. Minus 2 angle 0 degrees amps. Oops, and this is also control equals to 0. Much like I did way back when we were doing MathCAD for solving nodal and mesh problems in DC circuits, I'm going to store everything in an array. So here's V1, V2, V3, V4, V5, V6. I did it again. Vx, Ix. Solved everything for me. Now, I want you guys to notice something. By default, MathCAD gives us the answer in rectangular form, where it's using I as the imaginary operator, right? So if we go to this math formatting tab here, and this area right here, this button that says 1 + 1i, this is how we can change the form of the complex values. So this is just a drop-down menu, and I want you to notice all of the different options that we have, right? So that topmost option says 1 + 1i. So effectively what that means is it's going to give us the answer as a rectangular form complex number with I instead of j, which gross. The second option is 1 + 1j, meaning that it's going to give us the number in the rectangular form that we as future electrical engineers would use, okay? The one immediately below that, so the middle option, gives us 1.141 with an angle of 0.25 pi. So this form is effectively polar form with the angle expressed in pi radians, okay? The option below that doesn't have the pi, so that's the angle, it's a polar form with the angle expressed in radians. And then finally, the bottommost option is polar form with the angle expressed in degrees, which is what we will generally use for most of our things. So these are the results that we got using nodal analysis. For problem 2 on this in-class assignment, you're expected to do a similar thing using mesh. So my question to you guys is, do you want me to review mesh with you, or are you good to do that on your own for a couple of minutes while I set the lab up? Okay, well, I got one person saying they're good to do it on their own and nobody else is saying a damn word, so I'm gonna go with Camden. All right, the mini lab assignment sheet is up, so you guys can start working on that now if you want to. One thing that I want to point out to you guys, if this thing will load. Oh no. All right, that's annoying me, so I'm just gonna open the damn thing up. We'll be here. Close this out. So you're asked a couple of questions here. And I guess they aren't as leading as I would prefer. So you got a bunch of setup stuff. Then you're asked from the graph, does the current lead or lag the voltage across the inductor? And I specify if you followed things, the yellow line is the voltage drop across the inductor. The white line is the graph of the voltage drop across the resistor and thereby the current. What I'm asking in the next question, if you change the frequency of the function generator from whatever its original setting was up to 50 kilohertz, how does it affect the output? What I'm looking for is the magnitude of the voltage larger or smaller, is the magnitude of the current larger and smaller. Because you have a RL network, the current should always lag the voltage. That isn't going to change, and it's actually not even going to change by what angle. It's always going to be pretty darn close to 90 degrees. What I'm asking you here really is, what is the impedance doing, right? So for this first circuit, we scroll up here and look at it. If that resistor, or excuse me, if that inductor L were a resistor, this would just be a simple voltage divider network. So all this is a voltage divider in the frequency domain, okay? Because we are changing the frequency, the impedance of that inductor is going to change, right? So at very low frequencies, the inductor is going to have a small impedance because it's proportional to omega, which means we should see a relatively small voltage drop and a relatively large current. As the impedance of the inductor increases because we increased our frequency, we're going to see a larger voltage drop. Ohm's law tells us that the voltage drop across an element is proportional to the size of the impedance. And then we're going to see the current be smaller because there's a larger total impedance seen by our source voltage, right? So what we're really looking at here is just how the impedance changes as a function of frequency and what impacts that has on the current through that inductor and the voltage drop across that inductor. And then we do the exact same thing for this network where the inductor was replaced by a capacitor. And you should see that since the capacitor's impedance is 1 over j omega c, or inversely proportional to the frequency, it has the exact opposite effect, right? So an increase in frequency for the inductor should make voltage go up, current go down. An increase in frequency for the capacitor should make voltage go down, current go up. So that's what I'm looking for. So, all right, I will let you to it. And I'll put the math CAD back up in case anybody still needs to look at that for whatever reason. If you have any questions about anything, ask, I'll be happy to answer them.